Hello everyone. Today we are covering a topic from IGCSE Cambridge Chemistry, lesson Organic Chemistry, topic Formula, Functional Groups and Terminology. We know by now that in organic chemistry we talk about compounds made of mainly carbon, hydrogen and oxygen. Depending on the number of carbons in the compound and the functional group, there are many different organic compounds. So it's important to indicate both the number of carbons and the functional group when naming the compound. To do this, we use the prefix and the suffix of the name. The prefix is how the name starts, and that will indicate the number of carbons. For example, if there is one carbon, the name will begin with the prefix meth. If it's 2, then it will be eth. 3, prop. And it's 4, but. And if it's 5, then hen. The suffix or how the name ends will indicate the functional group. For example, if it is an alkane, we end with ane. If it is an alkene, we end with -ene. If it is an alcohol, then we end with -ol. Finally, if it's carboxylic acid, then we add oic acid to the end. So let's just take a very quick example. If it is an organic compound, which is an alkane with one carbon, we called it methane or methane. If it is an alkene with 2 carbons, then it's eth and ene. So it becomes ethene. If it is an alcohol with 3 carbons, then we start with prop, end with -ol. Becomes propanol. And then if it is a carboxylic acid with 4 carbons, it would be butonic acid. Butonic acid. To make things easier, we define something called a homologous series. A homologous series is a family of similar compounds with similar chemical properties due to the presence of the same functional group. It means the organic compounds with the same functional group are grouped together and we call it a homologous series. And because of the same functional group, they would have similar chemical properties within that homologous series. There are 4 main homologous series that we need to know in this syllabus: alkanes, alkenes, alcohols, and carboxylic acid. And here, the general formula for each of these homologous series are given. Alkanes, it would be CnH2n+2. This N is always the number of carbons. So the only thing in a homologous series, the only thing that changes is the number of carbons and therefore the number of hydrogens as well. And then for the alkenes, we have the general formula CnH2n. For alcohols, it is CnH2n+1 OH. OH is the functional group that is common in alcohols. Finally, for carboxylic acids, we have Cn-1 because, see, one of the carbons, we already mentioned it outside. H2n+1, COOH. COOH is the functional group of carboxylic acids. In alkenes, the functional group is a single carbon-carbon double bond. One carbon-carbon double bond. And for alkanes, the speciality is that there are no double bonds or triple bonds. All carbon-carbon bonds are single bonds. And alkanes are only made out of carbons and hydrogens and nothing else. Now, each organic compound in the same homologous series will have similar chemical properties, which means they would undergo the same chemical reaction when they meet the same reactants. Now, for example, all alkenes, regardless of whether it has 2 carbons, 3 carbons, 10 carbons, all alkenes will decolorize bromine water from orange to colorless. So if you put bromine water into a sample of alkenes, whether it is 2 carbons, 3 carbons, or even 10 carbons, you will see the same result of the bromine water going from orange to colorless. And this is because of the presence of the carbon-carbon double bond. Whereas alkanes, every single alkane, none of it decolorize bromine water because they don't have a carbon-carbon double. No alkane will have carbon-carbon double. So every single alkane will react to bromine the same way, which is having no reaction. Basically, it will not react with bromine water because it doesn't have a double bond. Within the same homologous series, the organic compounds differ by a unit of CH2. For example, let's take an alkane. We'll take ethane. Ethane, if you write the formula, it would be C2H6. After ethane, if it's 3 carbons, what is it? It is propane. Propane will have 3 carbons and 8 hydrogens. What is the difference from ethane to propane? 1 carbon and 2 hydrogens. Exactly CH2. This is what I mean by the difference of 2 consecutive members in the homologous series is always CH2, a unit of CH2. Now, although the different compounds in a homologous series don't have the same physical property because the physical properties depend on the number of carbons in the carbon chain. Although that is the case, in the same homologous series, the physical properties would share the same trend. Of course, it won't be the same like chemical properties, but they would have the same trend. Another classification of organic compounds are saturated and unsaturated. At this stage, to differentiate between saturated and unsaturated, we are only looking at the carbon-carbon bonds. You should know by now, carbon can have a maximum of 4 bonds. Why? Because carbon needs exactly 4 electrons to complete the last electron shell. In an organic compound, you will find carbon-carbon single bonds, carbon-carbon double bonds, and even carbon-carbon triple bonds. There would never be 4 bonds because then it won't be organic. Because for an organic compound, you have to have carbons and hydrogens. Just carbons won't work. So you'll encounter these 3 types of bonds in organic chemistry. But in IGCSE, you will only be dealing with carbon-carbon double bonds and single bonds. Any compound with only carbon-carbon single bonds are called saturated compounds. And any compound with at least one, so not all the bonds should be double, but even if it has at least one double bond, it becomes unsaturated. Now, why do we call them saturated and unsaturated? I'm sure you have heard the word saturated before. What does it mean to have a saturated liquid. If there's a saturated solution, that means the maximum amount of solute that can dissolve in the solvent is already dissolved. Can't dissolve anymore. The maximum is already reached. So it's very similar when it comes to organic compounds. It means the maximum number of atoms that can bond with carbon had already bonded with carbon. So one carbon is bonded to 4 other atoms. So there's no way a carbon can bond with another one. This is why when there are only carbon-carbon single bonds, we call the atom or we call the molecule saturated. When it's unsaturated, there is a double bond, which means carbon is not bonded to 4 different atoms. Carbon is only bonded to 3 atoms. Let's consider this carbon. It has let's say it has one hydrogen from this side, one hydrogen from this side, but a double bond with a carbon. So it's only bonded with 1, 2, 3 atoms. If the carbon can break this double bond, it can add 1 more atom into the molecule. So an unsaturated organic compound is when there is room for some more atoms to join the molecule. Now let's look at the different ways we can represent organic compounds. Out of the many different ways, one is the general formula. Now we briefly spoke about the general formula before. A general formula is common for a homologous series. Each homologous series has its own general formula. When you know general formula and the number of carbons of a particular compound, we can find the molecular formula of that compound. For example, here, CnH2n. This is the general formula for alkenes. So if you know the alkene has 5 carbons, then you can find the molecular formula. It is C5H10. And here we have the general formula of alkanes. Again, it's the same thing. You just need to know the number of carbons, then you can find the molecular formula. Here, if the number of carbons was 5, then it would be C5H12. And here they have given the general formula of alcohol. Same thing applies here as well. If you know the number of carbons, you can find the molecular formula. In this case, it would be, if it's 5 carbons, C5H11OH. It's the molecular formula of pentanol. Next, we have the displayed formula. This shows every single atom and bond in the structure and how they are arranged. So for example, here they have given the displayed formula of butane. Butane is an alkane with 4 carbons. So they have drawn the carbons first, and each carbon has only a single bond with the other carbon. And for each of the other spaces, a hydrogen is attached. So we get the displayed formula like this. Then we have the molecular formula. Now, this gives us the exact number of atoms in that molecule. This is the most commonly used method in chemistry to represent any molecule, not just organic molecules, even inorganic molecules. It shows the type of atoms present and the exact number of each atom. For example, this is also for a butane. A butane would have 4 carbons and 10 hydrogens. Then there is the structural formula. The structural formula gives enough information to make the structure clear, but not all the bonds are shown. In the structural formula, we don't really draw and show single bonds. But very important bonds like double and triple bonds are shown. For example, here, this is the formula for a butane. A butane doesn't have any double bonds or triple bonds. So none of the bonds are shown, but each of the carbon and what is attached to each of that carbon is shown. For example, this carbon, of course, obviously it's attached to this carbon and 3 other hydrogens. This carbon is attached to this one and the one next to that, 2 other hydrogens. Now, say we want to represent butene instead of butane, then we would show it like this. So in this case, we don't show any single bonds, but still we indicate the double bond. And then finally, we have the empirical formula. This gives the simplest whole number ratio of the atoms present in the molecule. Now, later on, we will be learning how to exactly calculate the empirical formula of a compound. The final concept we are going to learn under this topic is structural isomerism. Now, there are some types of molecules with the same molecular formula, but different structures. So if you just look at the molecular formula, you'll see the same atom. That means the same type of atoms as well as the same number of each atom. But if you look at the displayed formula, then you'll see different ways to drawing the same molecular formula. Let's look at this example here. All of these examples show a pentane. So here, the number of carbons is 5, and number of hydrogens is 12 in every single one of these examples. But in this first molecule, they have arranged the carbons one after another like a chain. So each carbon is only attached to maximum of 2 other carbons. And then when you come here, it's different. There's a chain of 4 carbons and 1 carbon is attached to one of the middle carbons. So if you look at this one, this carbon is attached to 3 carbons and 1 hydrogen. But still, the total number of carbons is 5. The total number of hydrogens, if you count, it's going to be 12. And there's another way of drawing it. There's 1 carbon in the middle and 4 carbons are attached to that 1 carbon in the middle in all 4 directions. So this carbon here is only attached to carbons, other carbons. And the hydrogens are placed on the carbons around it. Still, we have just 5 carbons and 12 hydrogens. So in the exam, you would require to draw different isomers for the same molecular formula. Now that we have covered the theory for this topic, let's have a look at a few past paper questions. Which of the following statements is incorrect? Now, we have given 2 molecules, A and B. Statement 1 says empirical and molecular formula of A and B are the same. A is unbranched, B is branched. A and B both belong to the same homologous series. A and B both can be isomers. So just by looking it, we can confirm one thing. Both A and B has the functional group OH. Because of that, we can say that A and B both belong to the same homologous series. We can pick this one. To answer the others, especially the first one and the fourth one, we need to know the molecular formula. So let's find the molecular formula of A. A has 1, 2, 3, 4 carbons. C4. And how many hydrogens without this OH? 3, 4, 5, 6, 7, 8, 9. Has 9 hydrogens and of course the functional group OH. This is A. Then let's look at B. B has 1, 2, and 3. Is it just 3 carbons? No. Look at this. They have put this bracket to CH3 and then you have a subscript 2, which means there's 2 CH3s here. There's 1, 2, 3, 4 carbons as well. What about hydrogens? Inside the bracket, there's 3, and because it's 2 times that, there's 6 hydrogens. 6, 7, 8, 9 hydrogens as well. And of course, the functional group OH. So in fact, they do have the same molecular formula. This is correct. And because they have the same molecular formula, they can be isomers. But we have to see whether they have the same structure or different structures. Clearly here, A is talking about a carbon chain that is connected one after the other. This carbon is connected to one carbon. This carbon is connected to this first carbon and the third carbon, and the chain goes on. But what does this bracket mean? If you see a bracket like this means 2 CH3s are connected to this one carbon, which means there is a carbon that has 2 CH3s connected from either side, one hydrogen, and then only comes this CH2 from this end, an OH. This is what molecule B looks like. Whereas molecule A looks like this. There's CH3, and then there is just CH2, 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 and OH. So, as you can see, A and B, they have different structures but the same molecular formula. So, indeed, A and B are isomers. Let's go to statement 1. Empirical and molecular formula of A and B are the same. Yes, the molecular formula is same. Is the empirical formula same? Of course, if it has the same molecular formula, then it will definitely simplify into the same empirical formula. Okay, so if you just write the number of carbons, hydrogens, and oxygens, it would be C4, H10, and O. This is the simplest whole number ratio of the atoms. And empirical formula is also the same. So statement 1, 3, 4, they're correct. Too early then, statement 2 should be wrong. Let's check why it's wrong. The statement is saying A is unbranched, but B is branched. Is that what has happened? No, in fact, B is the one which has branches. A doesn't have any branches among the carbon-carbon bonds. So the incorrect statement is statement number 2. Let's look at one final question. C3H8 belongs to the homologous series of. Okay. Just by looking at the molecular formula, how would we guess the homologous series? This is where the general formulas of each homologous series comes in handy. So we have 4 homologous series that this could belong to. Either alkane, alkene, alcohol, or carboxylic acid. But alcohols and carboxylic acids are very easy to identify. Alcohols have the functional group OH, and carboxylic acids have functional group C double bonded O and OH. Or when we write the molecular formula, we write it as COOH. If you see either of these, right away you can say this is an alcohol and this is a carboxylic acid. But the molecular formula here doesn't have oxygen at all. So it can't be an alcohol or a carboxylic acid. Then the other 2 options that remain is alkenes and alkanes. We have not learned about alkynes, so you can cross that off as well. What is the general formula for alkenes and alkanes? For alkanes, the general formula is CnH2n plus 2. This alkane. And for alkene, we have the general formula CnH2n. So we just have to find whether this molecular formula belongs to the general formula of alkane or alkene. Here there are 3 carbons and 8 hydrogens. So twice of 3 is 6. If it was an alkene, it would be C3H6. But it's not C3H6, it's C3H8, which means the number of hydrogens were formed by 2n plus 2. Because 2n is 6 plus 2 is 8. So C3H8 actually belongs to general formula of an alkene, CnH2n plus 2. So this molecule is in fact an alkane and not an alkene. So the correct answer here would be answer 3, alkane. With this, we have come to the end of the discussion of this topic. Thank you for listening.